Hi, how's it going? My name is Gary. This is a guide on how to use the Ray integration for NVIDIA Isaac Lab. I'm about to jump right in, but I have to give two important disclaimers. This is an independent production. All of the views, opinions, and content expressed in this video are solely my own and do not reflect the views or opinions of any affiliated organizations, companies, individuals, as well as my employers, current, former, and future. This video is all me. I'm sitting in my bedroom right now, so it's all my responsibility. That being said, with great power comes great responsibility. I'm going to ask that if you learned something from this video, that you use that constructively and to help people. I apologize in advance if this video isn't super smooth. I'm trying to do it all in one take, kind of like a live stream, only with no live viewers. Maybe more of a speed run, not including Docker build times because that takes forever. All right, so jumping right in, I have this kind of a big PR here that adds Ray support to the NVIDIA Isaac Lab project. If you're not familiar with Isaac Lab, it's a framework for simulation for reinforcement learning and imitation learning. And the Ray support is not currently merged into main, but it's available on my fork right here, so you can just clone my fork and then check out this one feature branch. All right, so why might you want to use the Ray integration? So looking at Isaac Lab, there are a lot of great example environments, such as, let's pick one at random, like this walking robot environment. And when you take a look at that environment, there's the simulation code, which makes sense. And there's also the code for the reinforcement learning agent or network as well. And so taking a look at this code, you can see that there are a lot of parameters in the neural network, such as the number of layers and how many neurons are in each layer. And you might be wondering, how do the maintainers of Isaac Lab come up with these values? And oftentimes it's very much intuition or trial and error. And this isn't always the most effective way to come up with these values. And kind of the point of the Ray integration is so that you're able to empirically test a bunch of different values for, say, the number of layers, the number of neurons, and determine experimentally what's the most optimal network structure for your specific environment. And the code that does a lot of the heavy lifting that is the same if you're running the Ray integration locally, or if you're running the Ray integration, say, on a Kubernetes cluster, is this Isaac Ray tuner. And kind of jumping right in with a local example, let's say that you have a computer that has many GPUs. So there are a few prerequisites that you're going to want. You're going to want the CUDA to be installed, as well as the NVIDIA driver. I recommend Linux, and I also recommend installing CUDA/the driver from the run file. In my experience, installing it in this manner is kind of the most reliable. And you're also going to want to have followed the Docker setup instructions, which we can grab right here super quick. Yeah, so follow this Docker guide and make sure that the default Docker works with the NVIDIA Container Toolkit. And so you can build it with start. I've kind of cheated it and built it behind the scenes. And then you can also verify that the kind of base Isaac image works. And the way you can verify that is by running NVIDIA SMI and seeing that all of your GPUs are available. In this case, I've got a VM with 8 NVIDIA GPUs, but this would also work with a local computer with 1 NVIDIA GPU. The next thing that we're going to do is we're going to build the specific Ray integration, which has some small trickery to do with paths and whatnot. I'll show you the Docker file for that really quick. There it is. So you can see this just installs Ray and make sure that it uses the right executable. And it also installs some other dependencies such as MLF Flow, which actually isn't needed for local development, but that'll come in handy for any development on a cluster. So I've already built that kind of improved image, and with the Ray stuff, I mean. And then what we're going to do is we're going to run the Ray image that I built. Oh, misspelled Docker there. Oops. Okay, perfect. And then we're going to check, just for the sake of sanity, that NVIDIA SMI works, and it all works. And then we're going to follow the ReadMe that is built in to the array integration. So this isn't merged into main yet. Hopefully it will soon, but you can still view this on my fork. And there's a one-line command for local or VM, setting up the array cluster that is going to be able to accept the jobs, such as a bunch of different training runs that all have different hyperparameters, so that you can try all of them and see what's best. So we're going to start the server here. The next thing we're going to do is we're going to locate where that image is that we're running. You can see that it's got this container ID. So we're just going to exec to start a new terminal. And then looking at that tune file that I was showing earlier, kind of the Isaac Ray tune, there's an example for local. Out of the box, this doesn't actually tune anything. It just runs a carpal example, but it's pretty good to test that everything works. So we're going to copy this over. And one important note is that by default, we're going to assume that each node has one worker, or each computer has one worker. And in the case where we have one node, one local computer, or one VM node that has more than one GPU, and we want to be able to utilize all 8 GPUs in parallel, we're going to have to specify that. We're going to say num workers per node is going to be 8, meaning that for each worker, they're going to get 1 GPU, meaning that we should be able to run 8 trials in parallel. And kind of a question that I personally would be curious about if I was watching this video is, what's this config file look like? How do you actually test the different hyperparameters? That's a great question if I say so myself. And the way that the varying of the hyperparameters works is it takes advantage of the existing Hydra configuration system. So there's this existing system where you're able to change kind of the values in that param file kind of in this sort of way that I showed, the param file being this. And setting that up, what that really looks like, I've got an example for the Vision carpal environments because I contributed to those. So you can see here, I have some examples right out of the box. You can vary the environment count as well as the batch size and horizon length. And you can see that you vary it using that kind of Hydra syntax. I got another example for varying the convolutional neural network structure, again, using that kind of Hydra syntax, using the Ray Tune API for actually varying the values themselves. And so that's what you can see here with like the tune.choice or the tune.randint. And I've also got an example for varying the multi-layer perceptron. And I've also got examples for varying kind of the feature extraction models that are in the carpal examples. Then you can see here, I override the task, telling specifically what task I want to tune on. And so we're going to do a small example here with, let's say, the CNN only. I'm going to copy this. Okay. I'm going to paste this in. Okay, and then I want this to be able to finish during the duration of the video. So I'm also going to define the number of samples, which should be somewhere in here. Okay, num samples. Yeah, that makes sense. And let's say that we're going to run 16 samples. So each worker should be dispatched twice. All right, so you should see in a second that all of the workers are being used. And the way you can tell is that the GPU count, the GPU utilization should really spike here in a minute. So you can see one job was issued, a second job was issued, and so on. And you can see kind of the output up here. And like I said, this will work for if you have one GPU, if you want to like leave your computer running over the weekend, testing a bunch of different hyperparameters, you can totally do that. And this will take care of, dispatching the jobs, starting the experiments, ending the experiments, logging the experiments and whatnot. And after all these, spin up, you can see that, I've got 8 jobs running at once. They're all trying very similar setup, but I promise that the CNN is being varied. You can see it's using all the CPUs on this computer, and it's using all 8 GPUs, and it's running 8 jobs in parallel. And you can tell by kind of looking at that stack trace. But this is for one node, and one node can only have so many GPUs. You can only put so many GPUs into one computer. And that's where the Ray cluster integration comes in. So say you have access to a Kubernetes cluster, and you have 32 nodes, and each node has 1 GPU, well, you can also take advantage of that very similarly. Out of the box, I have this set up for GCP, Google Cloud, with the container service, the Google Kubernetes engine. And so the thing that's important in this kuberay.yaml.jinja, this is templated so that you can set up the cluster, the Ray cluster in any way on top of the existing Kubernetes cluster. The important parts is that you also include an ML Flow server. This is for fetching the logs. And the reason I did that is because ML Flow is free, unlike WANDB, which is costs money for corporate licenses. And to get the cluster version set up is incredibly similar to how to get the local/VM version set up. So we're going to switch to a different VM here. You can see that I've only got 1 GPU. And we're going to assume again that we built the base container, that the base container works, that we built the Ray specific container, and I'm actually going to show that right now. And so I've got this kind of secret. This should be like a container registry / like the name of the container, because we're going to push this up to artifact registry so that we're able to create the cluster. So I'm going to run this, and I'm going to dump this file into this file.txt that I'm going to edit the secrets out of super quick. And on the last take of this video, I didn't edit out the secrets, and I had to restart the video at like 10 minutes in, which made me sad. So we're gonna do that correctly this time. Okay, I just edited out the secrets. You can see that this built successfully, and I've got no secrets. And then what we're gonna do is we're gonna push this up to our container registry, which should be set up so that your computer has access to the container registry. Again, we're gonna log it to the secrets file. Here, I'm gonna delete the file real quick so that I'm able to cat it and it won't be like everything. Just doing some magic off screen here. Okay. And that should work, I hope. Okay. Hopefully it's pushing the updated image to the registry, and once this finishes in a second, I'll be able to cat that output file, and it should be fine. In the meantime, what I'm gonna do is I'm gonna show kind of what the output of the Ray stuff works. So you might be wondering, like, after I run all this Ray stuff, you can visualize it with TensorBoard, all of these different runs. And so this is kind of a run that's already finished that could be generated via the cluster or via local computer. And you can see here that there are some runs that do a lot better, and these have like a lot different network structure. And once you identify the name of a run that is doing well, then you can look at the logs to find out exactly what hyperparameters were used, what structure the network has, and whatnot. And it's a nice visualization of everything in parallel. All right, so it looks like that finished. Gonna edit this real quick so that it doesn't include the image name, and I'm gonna show you what that looks like. And I'm gonna really hope that I edit out the image name correctly again. Doing that off-screen magic. I don't know if that's important. Okay, I'm just gonna delete it. So then I'm gonna cat that file.txt. Okay, we see that we've pushed this image to an existing registry. And so now we're gonna create the Kubernetes cluster. And I have this set up for GCP, but if you make a similar kuberay.yaml.jinja that is specific to AWS or something like that, it should very much still work with everything else that I'm going to show in this video, which includes the Grok cluster with kubectl, the Ray tune, as well as the submit job, and downloading the logs once everything has finished. So I'm going to spin up this cluster, and I hope I have the command. Okay. Boom. So I have the image name, and so you can see that this is using the source standalone workflows Ray launch. When you run this, you should run this with the Isaac Lab.sh file. I've got that in the ReadMe. you should first kind of install all of these dependencies and whatnot. And then once you run the file, in that launch file, I have an example of exactly how to spin everything up and whatnot. So what we're going to do is we're going to spin up our cluster here using that image that we built earlier. You can see num workers is 8. I kind of want to set it to like 9 or something just to show that it's different from the other file, but I'm scared it won't get provisioned. But let's live dangerously here. Using the NVIDIA Tesla T4, you could change this to L4, whatever is available. 12 CPUs per worker, 20 gigabytes of RAM per worker. Okay. You can see that it's created the array cluster as well as the ML flow for fetching the logs. And so we can check up on this using kubectl. Okay, I'm scared about these that are pending. Sometimes they don't get provisioned correctly. Not sure what we can do in the meantime. I might just have to cut until those get provisioned, unless I can find something else that's exciting to talk about. All right, we're back. I want to pretend like my cluster did not get provisioned, but to be perfectly honest with you, I found a mistake in my own documentation that tripped me up pretty bad, so it took a minute to figure that out, but I pushed up the fix, don't worry. So we're going to check that our cluster is running with kubectl get pods. You can see that the status of all of these is running. Then I have a nice script here called grok clusters. Normally you'd run this with the Isaac Lab.sh, but I'm just running this on a computer with no GPU. So I'm replacing that with Python. And what this does is it pretty much just gets the address of the head of the array cluster. And you don't need to use Kubernetes to spin up such a cluster. You could do this with pure array. The only thing is that you need to generate this config file, which just has the contents of the address of the cluster you're submitting jobs to. Another important point about this grok cluster is that it gets the ML Flow address. So this is for retrieving the logs. And this would work if you created a Kubernetes kubearray cluster with another cloud service provider. The grok clusters should still work if you set up your kubectl context and namespace and whatnot. So what we're going to do is we're going to use this submit script that's going to submit a job to the cluster. And this is actually what I just corrected and pushed the commit for. Importantly, we're going to put in the ML Flow URI right there. And I really hope this works because I just stopped this video for like 20 minutes while I figured this out. Okay, so we can visit the cluster kind of in our server. So you can see we've got all these workers. We got, all 10 workers that we requested. And then hopefully this job should be running. And so you'll see that you can read this log. And so you can see all of the commands that it's using. This is kind of like a very valuable debug thing. Like if these jobs are failing, you can paste these kind of in your local computer to try the same job and see what's going on. So in a second here, once it's dispatched all the jobs and it's warmed up the cache, we should see that, that all of the GPU utilization has gone up. And you can see here it's starting to, compute some things, starting to load up the jobs. Once the jobs have been dispatched correctly, which hopefully should happen, I really hope, the output of this is very similar to what I was showing earlier with the local. You can see that we got several jobs running in parallel using 8 GPUs currently. And once this is finished running, we can recover kind of the logs and everything by port forwarding the ML flow address. We can do that just like this using kubectl. So we're going to port forward that. And then we should be able to visit that now to see the ML Flow Dashboard, localhost 5000. And you can see that I have a bunch of runs that started. And once these runs finish, I'll be able to see all of the relevant information here. If I want to see the hyperparameters that are related to these runs, I can just click on them and expand parameters. This is kind of the basic test example where there aren't any varied parameters, but if you wanted to use a different example, you would just pass it in the config class, or you'd write your own configuration file that's similar to this Vision carpol example. So we can see here that the cluster hopefully should be working. Okay, the VRAM is starting to fill up a little bit. You can see the utilization start to fill up a little bit, and in a second, yeah, you can see the first job started, and you can continue to monitor the logs from here. So you may be asking, like, ML Flow is great, but what if I want the logs on my local computer and not on this like ephemeral like Kubernetes cluster? And in order to download the logs, you can use this kind of nice ML Flow to local TensorBoard.py. It has very, very simple. You just enter the URI and the experiment name that you read off of the dashboard right here, which you can copy and paste just like that. And then you can just run that. And an example for running that is right here. So that kind of covers it. I mean, if you have any Kubernetes, Ray, NVIDIA Isaac Lab questions, just at my GitHub, at Gary Levove on the main issues page for Isaac Lab, and I should get around to it when I have a chance. Thanks.